Welcome back to Honors Calculus. In this video, we're looking at indefinite integrals and antiderivatives. We've seen previously that an indefinite integral is going to be a family of functions, all of whom satisfy some properties about their derivatives. Let me get my head out of the way and let me summarize what we're talking about here. If I define some function capital F of x as the indefinite integral of little f of x dx, first of all, the thing to remember here is that I don't get a single function. I get a family of functions, big F of x plus c, for any constant c. Every distinct value of c is also correctly the solution to the indefinite integral. And the property in question is that the derivative of capital F of x is equal to lowercase f of x. And that gives us a strategy. If we can find any one function, capital F of x, so that its derivative is little f of x, then we know that every other function that satisfies that is just the difference of adding or subtracting a constant. So it doesn't matter which one we find as long as we find one. Sometimes that's easier said than done, but sometimes it's pretty straightforward. So for example, if I want to try to figure out the indefinite integral of 3x squared minus 2x dx, then I'm going to try to take a guess at what capital F of x is going to look like. And I've got a couple of terms here, right? I've got two terms. So that informs my guesswork. I know that I want to guess something that's going to result in two terms. And I can look at each of these two terms and think about them on their own. Right? What kind of function gives me a derivative that is x squared? Well, result of x squared tends to come out of the power rule, right? Reduce the power by 1, multiply by the thing in front. So to get something involving an x squared, I probably want something involving an x cubed. To get something involving an x, I probably want something involving an x squared. And again, I know that this is differentiation, and I know that if I add any constant to this, it's not going to change anything. So I'm going to include that plus c now. Then I check. I take the derivative of my guess. The derivative of x cubed is 3x squared. The derivative of x squared is 2x. The derivative of a constant is 0. and I have 3x squared plus 2x. Well, that's close to what I wanted, but not quite there yet. I need to do something a little bit better. Specifically, I need that minus that I've already circled when I was talking about the fact that there's two terms. I need that to be a minus. I ended up with a plus. All right, so if I want that to be a minus, well, that was this plus sign. So let's try making that a minus instead. My second guess is that f of x is x cubed minus x squared plus c. I can check again by taking the derivative. I get 3x squared minus 2x, which is exactly what I said was supposed to happen there. And so on my second guess, I nailed it. Let's take a look at one more example like this. Let's say that I want the integral of 5x cubed dx. Well, I'm going to make a guess. I am going to guess at what kind of function has a derivative that comes out as x cubed. Well, that's polynomial. It's just one term. That makes life a little bit easier. All right, well, what kind of things happen with derivatives on polynomials? It decreases the power. So to get an x cubed, I probably wanted to start with an x to the fourth power. And if I add an arbitrary constant onto this function, it's not going to change anything because when I take the derivative of x to the fourth is 4x cubed. The derivative of a constant is 0. All right, so I got 4x cubed. I needed 5x cubed. It looks promising. It's somewhere in the right direction. But it didn't quite work. So let's try a second guess. Well, one thing I know about derivatives is that if I multiply a derivative by a constant, or if I multiply a function by a constant, the derivative gets multiplied by the same constant. So I want 5, I had 4. I could try multiplying by 5 over 4, because 5 over 4 times 4 is 5. So let's try 5/4 times x to the fourth plus c. And here's where I get to be a little bit cute, because if I distribute here, right, the 5 to the fourth times x to the fourth is 5 to the fourth x to the fourth. 5 to the fourth multiplied times an arbitrary constant. Well, if the constant is whatever I want it to be, and then I multiply by 5/4, that just means I had to have chosen the constant a little bit more carefully in the first place, but I can still get that result to be anything I want it to be. It's still an arbitrary constant. All right, so we tried differentiating here. We'll have 5/4 times 4x cubed, and the derivative of a constant is still 0. The 4's cancel each other out, leaving me with 5x cubed, which is exactly what I said I wanted. So on my second guess, I got it right. Right. If you are very comfortable with derivatives, you will start to learn to recognize some of these at the first try without having to go any further. If you're a little bit less comfortable with derivatives, it might take you 2 or 3 or even 4 guesses to refine your result to get where you need to be. In upcoming videos, I'm going to look at some tricks we can use, some patterns we can recognize to streamline this process to make our lives easier. But for right now, I'd like you to practice just this guess and check approach. Sorry, I wrote down the wrong problem as I was writing that down. Use a guess and check to evaluate the integral of 3x cubed minus 4x dx. All right, take a few minutes, play around with the fundamental theorem, play around with this idea of antiderivatives, see what you get there, and I'll see you in the next video.